Okay, good morning, everyone. Today, we are very happy to invite Dr. Yonglong to come to give us a talk. Dr. Yonglong got his bachelor degree in mathematics in Zhengzhou University in 2011 and got his PhD in Hong Kong University in 2015. Both are from mathematics department. And during 2015 to 2017, he worked as a research assistant in the mathematics of University of Hong Kong. And from 2017 to 2019, from till now, he worked as a postdoc in University of California, Santiago. And from 2019 till now, he worked as a research fellow at University of Singapore in the group of the Dr. Dan Yanfu Vincent. So let's welcome him.
Okay. Good morning, everyone. It's glad to be here to give a talk on my work. Can you hear me?
Yes, we can hear you.
Okay. Today I'm going to talk about sequential quantum hypothesis testing. This is a joint work with Vincent and Marco. Okay. This is the outline of the talk. First, I will introduce the background, the problem setup, and the background on quantum hypothesis testing. Then I will introduce our problem formulation for what I call sequential quantum hypothesis testing. Then I will state our main results. Our main result is about the characterization of the exponents, the optimal exponents for sequential quantum hypothesis testing. Okay. So then I will show you some numerical examples to show that sequential is actually better than fixed length, even better than collective measurement. Okay, if we still have time, I will tell you some main ideas of the proof. Okay. Now let me give okay, this is some notation we'll use throughout the talk. Okay. So in this work, we only consider finite dimensional Hilbert space, which is the d-dimensional complex Euclidean space. So the quantum state in this we consider is a mixed state. So it's a d by d positive semi-definite matrix with trace 1. So this is whenever we have a quantum system, if we want to observe the quantum system, we need to perform some measurement. This is captured by the notion of positive operator valued measure. Okay, this is defined as the set of here we only consider finite dimensional setting. So this is POVM is a set of matrix. This matrix, each one is positive semi-definite. Their sum is equal to the d-dimensional identity matrix. Okay. So a special class of POVM, which is very important, is the projector valued measure, which is the PV. I will use the shorthand notation PVM. Okay, so PVM is the POVM with the additional assumption that each one is actually each matrix in the elements of a POVM is actually a projector. So the square of itself is equal to itself. Okay. So if the quantum state is prepared, if the quantum system is prepared in state rho, and we apply the POVM M to the system, then the probability that obtaining the outcome X is equal to the trace of the product of rho and mx. Okay, so this is the basic notion that we'll use throughout the talk. Okay, So two other divergence which is very important to this work. The first one is the quantum relative entropy. Okay. So I think most of you are quantum people, so I no need to introduce this one and this one. Okay. So for two quantum states, rho 0 and rho 1, if they have the same support, then we can define the relative entropy, which is a finite quantity, otherwise it's infinite. This is defined as the trace of the product and the difference. So this is a generalization of classical KL divergence in classical information theory. So another quantity which is very important in this work is the measured relative entropy. So the measured relative entropy originally is defined in this way. This is for two quantum states rho 0 and rho 1. The measured relative entropy is defined as the supremum of the classical relative entropy between the probability measures. This between two probability measures, this one and this one. This is the first one is the probability distribution induced when you perform the POVM on the quantum system, which is prepared in state rho 0. Okay. Similarly, this is the probability distribution. This is the probability distribution induced when you perform POVM on the quantum system, which is prepared in rho 1. Okay. So here the supremum is taking over all rank 1 projector valued measures. Okay. So the following theorem proved by Marco and his friend is give another.
So I'm somewhat confused by equation 1.
Okay.
So a script m appears on the left but not on the right.
This one?
That m on the left doesn't appear on the right.
You mean this m?
Yeah, it doesn't appear on the right.
It's appeared here. This m is
it's m in there.
Yeah, this m
Okay.
M is here. This is just denoted to be the measured one.
Okay.
M is the POVM. Okay. So this M is the all rank 1 projector valued measure. Okay. Theorem 2 is proved by Marco and his friend, which give another formulation is another equivalent definition of measured relative entropy. Okay. So the supremum in equation 1 is taking over all projector valued measures. The supremum in equation 2 is taking over all finite size and all POVM with outcomes in X. So this shows that equation 1 is actually equivalent to equation 2. Okay, those are two most important distance that we will use in the characterization of error exponents. Okay. Now let me tell you some basic things about quantum hypothesis testing. So the quantum system may be prepared in one of the two states. The first state is the tensor product of rho 0. The second possible state is the tensor product of rho 1. Okay, we try to figure out which state the quantum system is prepared. Then we perform a binary valued measurement, which is here is capital lambda n and in minus lambda n with binary outcome. Okay, to try to figure out the quantum system. So if the outcome of the measurement is 0, then we guess the quantum system is prepared in state rho 0. Otherwise, we guess the quantum system is prepared in rho 1. Okay. So then given a hypothesis testing problem, we can always define two kinds of errors: the probability of type 1 error and similarly probability of type 2 error. Okay. Here I use R of n to denote the type 1 error. This is the error that this is actually the probability that if the quantum system is prepared in row 0. However, the outcome of the measurement is 1. So you guessed the wrong. You didn't guess correctly. Okay. So this is the probability that you. This is the error probability that you make when you guess the wrong state. When you guess the system is prepared in row 1. However, the actual state of the system is row 0. Okay. Similarly, we can define the probability of type 2 error. Okay. This is the performance of a quantum hypothesis test. Okay. Below are some in the next 2 slides, I will give you a summary of the well-known results about the quantum hypothesis testing, phase-length quantum hypothesis testing. Okay. So this is the so the first one is the quantum Stein lemma, which is a generalization of classical Stein lemma. Okay. So this is the beta and epsilon is the infimum of type 2 error probability, subject to the condition that your type 1 error probability is bounded by some fixed number epsilon. Okay. So we try to figure out the behavior of this beta and epsilon when n goes to infinity. This will tell us something about the okay. So the quantum Stein lemma captures the asymptotic behavior of beta and epsilon, which is this equation. So when we take log, then we do the normalization, then we take the limit. This will converge to the relative entropy between row 0 and row 1. The quantum relative entropy between row 0 and row 1. So the second important result is the quantum Chernoff exponent. This is usually stated in the setting of Bayesian. Okay, so you have some. So here this is kind of like this is also kind of like we consider the sum of the error probability. We let Cn to denote the infimum over O length n test. Okay, of the sum of error probability. We also try to figure out the asymptotic behavior. This behavior is characterized by this equation. This is similarly when the error probability always goes to 0 exponentially. So we need to take the logarithm, then we do the normalization. Then we will see this one is actually converging to the Chernoff exponent, okay, which is defined in this way. Okay, the third one is the quantum Hosting bound. Okay, so this is the R is actually the kind of like the in information theory we always define achievable rate. So this is R is kind of like the achievable error exponent for all kinds of tests. Okay, this is kind of like so we say this is R0 R1 is in this set R if we can find a sequence of tests, not a single test, such that those two inequality holds. Okay, so then quantum Hoping bound give a characterization of this achievable rate region, which is in this form. Those three results are very well known in quantum information theory. Okay. So now let me all the results I talked about are fixed length results, which means the the number of states used during the test is fixed. Okay, it's each time you can perform a collective measurement, then you can get you get some outcome, then you make some decision. Okay.
Sorry, may I ask what's the R0, R1 here? Are they sequential measurement? I mean, you apply them several times, or
each time we just not several times, only one time.
then how do you take the limit? The limit is for the size or the measurement time?
Yeah, this should be, sorry, this should be, there exists a sequence of measurement, not a single measurement.
Okay. So you take the measurement limit to infinite.
Yeah.
Okay. So each time you apply either one, right?
Yeah.
Okay, thank you.
So all the results.
I also have a question. So if we specialize the case where row 0 and row 1 are both pure state, is it true that in this case it's simple because it's just the overlap to the power of n?
It's not true. Usually this kind of search theorem is assumed that the state has the same support. For two pure states, they don't have the same support size, so it's.
How do you define support here?
The support is kind of like for a mixed state. We consider the subspace generated by all the eigenvectors corresponding to non-zero eigenvalues.
I see. They have to have the same support.
Yeah.
Okay, I see.
Yeah, but I mean, even in that case, you could do some sort of a limiting process, right? I mean, you can take two almost pure states, and I mean, then the question would perhaps still hold. I mean, they would still have the same support, but you know, I mean, and full support or whatever you need. But you know, essentially, they are still pure states. Like it's just that you could still adopt some additional limiting process there as well, I think. But in any case, never mind.
Okay. Thank you. Okay. No, I can. The results in previous two slides are for state for the fixed length case. Each time the length of the test, the number of samples used during the test is fixed. Okay. Now I will going to talk about our work, the sequential case. Okay. So in this case, we assume there is an oracle who can prepare the quantum system either in row 0 or row 1. Okay. So then we assume there is an experimenter who can ask the oracle to prepare the state. He can ask the oracle to prepare the system. Then he can apply some measurement, the very general measurement to the system, and then he can make a decision. Okay. So like at time 1, the experimenter asks the oracle to prepare one single state, one copy of state row, and he randomly picks some measurement M1. He applies this measurement M1 to the quantum state and obtains the outcome X1. Then he tries to make a decision based on M1 and X1. Okay. So if he thinks he's confident to make a decision, he will output a non-star value. If the output of the decision function is 0, then he will say, oh, the quantum system is prepared in state row 0. If the output is 1, then he will say the quantum system is prepared in row 1. Okay. If he can't make a decision, then he will output a star. Then he will generate a new measurement randomly using this conditional probability mass function. Okay, so like at time 2, we generated M2, the new measurement, with conditioning on M1 and X1. As he can't make a decision, he is not very confident. Then he asks the oracle to prepare a new state, a new copy of state. Then he applies this measurement M2 to the new state. Then he obtains the outcome X2. Now he has two measurement and two outcome. Then he tries to make a decision based on M12 and X12. Okay, if he is confident, he output a non-star value. and stops the test, stops the experiment. If he is not confident, he output a star value. Then he generates a new measurement M3 based on the two measurements and the two outcomes. This process continues until the experimenter output another star value. Then the test is stopped. Then the experimenter stops the test and make a decision. Okay. So, any question about this? About this kind of formulation?
So I just miss. So the Oracle always prepares the same state, right? I mean, like if you prepare row 1, then you end up preparing row 1 in every subsequent cycle, right?
Yeah, the Oracle prepares the same quantum system each time. The state, but the experimenter don't know the state.
Right. Okay. And okay, fine. So actually, the number of events then depends upon the number of. So the number of events also depends then on the number of rounds. That is k. And okay, fine. Yeah. And okay, yeah, sure. And also what state was prepared. So you have two. Yeah. Okay. Thanks.
Okay. So the sequential here means that each time he can make a decision, and if he output a star value, he continues measurement. So the total number of states the experimenter requires from the Oracle is not fixed. It's actually a random variable. This is the key difference between the sequential quantum hypothesis testing and the fixed length quantum hypothesis testing.
Yeah, so there are totally how many variables? There are totally okay. So the guy who's doing the measure, sorry, yeah, the guy who's doing the measurement has two variables at his or her disposal. One is the number of rounds, and then the other is the type of measurement.
Yeah.
There are two random variables over here, and you want to optimize over that or whatever. Like you want to find out. Okay, fine.
Okay. Okay. So from this figure, we can define the notion of sequential quantum hypothesis test. Okay, we can see there are three key elements. One is the alphabet of the outcome X. The second one is the strategy to choose measurement based on the previous measurement and previous outcome. So this is this PK plus one. This PK is very important. Another one is the decision function. The decision function is a deterministic function of the measurement and the outcome. So those are the three key elements in a sequential quantum hypothesis test. Okay, so we define a sequential quantum hypothesis test in game. Okay, so this is the alphabet of the outcome. So PK is the sequence. PK is a sequence of conditional probability distributions. PK is a sequence of 0, 1 star value decision functions. Okay. So as I said, we can as I said, the number of samples used during the test is not fixed. So we let T to be the first time that decay is not equal to star. So T is the total number of samples or total number of rounds that the experimenter performed the test. Okay. So let me give you an example of what's a sequential quantum hypothesis test. This is a generalization of sequential probability ratio test. Here I call it a sequential quantum probability ratio test. Okay. So we define this sum as k. Okay, so if at time k we have output as 1k, we also have all the measurement m1k. Okay, so we define this log likelihood ratio. So if the underlying state is rho 0, then we know the expectation of sk will be blow up as k go to infinity. So when the underlying state is rho 1, the expectation of sk will go to negative negative infinity when k goes to infinity. Okay, so we will define two thresholds A and B. So we will look at the behavior of the log likelihood ratio. If it's very large, which means when it's larger than B, then we'll stop and output 0. If it's less than minus A, if it's very small, then we'll output 1 and stop the test. If the likelihood ratio, if the log likelihood ratio is between minus A and B, then we'll output a star value and continuous doing the test. Okay. So this is an example of a sequential quantum hypothesis test. Okay. So here we define T in this way. T is the first time that the log likelihood ratio is not in this interval, which means T is the first time we didn't output a star. Then we define this one. We include the T we include the T here. Okay, we will say this one is a sequential quantum probability ratio test with parameters A and B. This is an example of what a quantum test is. Sequential quantum test is. Okay, so in as you notice, you may notice that we actually the measurement we perform is local. So when we perform measurement locally, we can perform the measure even in an adaptive fashion or non-adaptive fashion. Here I define which means in an adaptive way, the measurement at time k plus 1 depends on the previous measurement, the previous outcome. If you choose the measurement in an non-adaptive fashion, then your measurement at time k plus 1 is independent of your previous measurement and previous outcome. Okay, so we will state our result. We will state our result for both adaptive strategy and non-adaptive strategies. Okay, so similar as the fixed length case, we can define the type 1 error and type 2 error. Okay, the type 1 error this is defined in this way. This is a probability that although the quantum system is prepared in row 0, however the output of the decision function is 1, which means you guess the state wrongly. Okay. So this is the probability of type 1 error. So similarly, we can define the probability of type 2 error. Okay. So in this work, we consider the asymptotic. We consider the asymptotic performance of a sequential quantum test. So we always consider a sequence of quantum tests. That's why here our test is indexed by n. The probability here, the probability and the expectation both are indexed by n. The I is used to denote whether if the underlying state is prepared is actually row 0, then we will use Pn0. Okay. So as in practical case, we can't do the tests forever. We need to have some constraint on the number of samples we use during the test. In this work, we consider two type of constraints on the number of samples we use. Okay, the first one is the expectation constant. As the number of samples used during the test is a random variable, so it's very natural to consider this kind of expectation constant. Okay, like we assume that the maximum of the expectation constraint. Sorry, the maximum of the expectation of number of samples is less than n. Okay. So the second one is the second type of constraint is the probability constraint, which means like the number of samples you use is larger than n should have a very small probability. Okay, so this is captured by this type of constraint. So as I said, in this work we consider the asymptotic performance of tests, and the error probability always go to 0 exponentially fast. So we try to find the convergence rate of the error probabilities. Okay, so we define this kind of notion, the achievable error exponent pair. So we say this one is an achievable error exponent pair, and the expectation constant. If we can find a sequence of quantum sequential hypothesis tests Fn, such that the equation 7 holds, which means R0 and R1 are lower bound of the convergence rate of the error probabilities. Okay, so equation 8 basically says that this sequence of tests should satisfy the expectation constraint asymptotically. Similarly, we can define epsilon achievable error exponent pair and the probability constraint. If we can find the sequence of quantum sequential hypothesis tests satisfy equation 7, and also this sequence of tests that also satisfies the probability constraint asymptotically. Okay. Okay. So based on the type of constraint you use, based on the strategy, the fashion of the strategy you choose, either adaptively or non-adaptively, then we can define 4 regions. Okay, so this is the AE. This is the region of all achievable error exponent pair and the expectation constraints using adaptive strategies. So AP epsilon, this is the closure of the This is the closure of the set of all epsilon achievable error exponent pairs under the probability constraint using adaptive strategies. RE and RP epsilon defined similarly, but the strategy you use is non-adaptive ones. Okay. So in this work, we will give 4 explicit characterization of those 4 regions. Sequential quantum hypothesis. This problem is very new. There are only 2 related papers. The first one is published in 2017. In this work, in the first paper, the author applied the sequential strategy to try to minimize the number of states you use, giving some threshold on error probability. Okay. So more related to our work is the very new one. They just published this year, and in this new paper, the authors more formally formulate the problem sequential quantum hypothesis testing, and also give some bounds on the performance of the test. Okay, so the first set of equation is for two vanishing error probabilities, type 1 and type 2 error probabilities, and if they use some fixed measurement during the whole process of test, then they have this kind of relationship between the expected number of samples and the error probabilities. This is captured by the first set of equations. Okay, the second equation is that the second is the lower bound on the lower bound for giving vanishing error probabilities alpha and beta. The author derived the lower bound on the expected number of samples during the test. No matter what test you have, you always should have this kind of lower bound. Okay. The question in their paper is that whether this lower bound is achievable is not addressed. So one of our main contributions of this work is that we show that there are actually a sequence of tests actually achieve this lower bound. Okay, so our test construct is actually optimal. Okay, so this is our main results. So our main result is theorem 3 is says that for two quantum states with full support, then for any epsilon larger than 0 less than 1, then we have this kind of characterization. So then we have this kind of characterization of the regions of achievable array exponents. The AP epsilon is equal to AE is equal to this one. This is a rectangle. Okay. So the corner point is formed it's given by the measured relative entropy. Okay. So this is we use the adaptive strategy that we can have. Okay. So compared with this the result in this year's CMRR paper, then we can see we are better, right? This is actually we can show that this one is this one holds as this one is the largest. This one from Marco and his front result, we know the measured relative entropy is actually the supremum of all of classical relative entropy over all measurements. Okay, so this one is larger. So this one is our bound is actually smaller than this one. So it's better. Okay, so our theorem 3 give a characterization of the achievable exponent pair when the experimenter each time requires a single copy of state. Okay. So if we allow the experimenter each time to require L copies of states, then we can define this similar problem. This is a similar binary hypothesis problem. Then we apply if we apply the similar analysis to our previous theorem, then actually we will see if the experimenter each time requires L copies of states, then we can see that this is the achievable array exponent pair. Okay, given this way. So if we try to get the ultimate quantum limit, we should let L go to infinity. Then we will see what we can, or what's the best we can do. Okay. So this is done through this important theorem proved by KI and Peace in 1991. Okay. So given two quantum states with full support, then the normalized measured relative entropy actually converts into the quantum relative entropy. Okay. So actually we have this one. So if rho 0 and rho 1 are two quantum states with full support, then the best we can do is given by this one. Okay. So R0 the R0 is less than the quantum relative entropy between rho 1 and rho 0. R1 is less than the quantum relative entropy between rho 0 and rho 1. Okay. So this is actually the best we can do. Okay, this figure summarizes the exponent for quantum hypothesis testing, both for the fixed length case and for the sequential case. Okay, so for the fixed length case, the red line here, this is the best you can do. This is the Hofstadter bound. This is the best you can do when you use fixed length collective measurement. Okay. So this point is when the two rate are equal, this is the Chernoff exponent. This one is actually the Stein exponent. Okay. However, when you pass to the sequential case, then this whole rectangle, then the point in this whole rectangle is achievable. So this give us this is the advantage. This is the advantage of sequential strategy over fixed length strategy. Okay. So our previous theorem are given for the give the characterization of the achievable error exponent pair for adaptive strategy. This is theorem 5 is a result for achievable error exponents when for the non-adaptive strategy. Okay. So this is the rho one if rho 0 and rho 1 are two quantum states with both poles, then the region is actually given by the closure of the convex hull of this C. So this is a little complicated. It's not very simple. So this is the C is given by this kind of union. The first union is over all finite alphabet. The second union is over all measurements with outcomes in this alphabet. Okay, those are the regions. Okay. So similarly, when we pass to the quantum limit, each time we ask the experimenter to require L copies of states, then we will have this one. This is the characterization of the achievable error exponent pair when we use non-adaptive strategies. Each time we require L copies. Okay. So 18 and 19 are the limit case, but here 19 is the limit case, but we don't have a very simple. We don't know the union of this set. We don't have a clear characterization of this union. Okay, so let me show you a numerical example. So this example is try to distinguish two qubit states, two qubit mixed states, rho 0 and rho 1. Okay, so psi I is psi 0 and psi 1 are two vectors. So you can think of rho 0 as this is a pure state. So you can think of this part as noise. When rho 0 is close to 1, this means the noise is the state is more close to a pure one. Okay, so here I is the 2 times 2 identity matrix. So for as rho 0 and rho 1 are characterized by parameter R0, R1, and theta. So to compare the performance of the optimal adaptive one and the non-adaptive one, we define two functions, f and g. F is the sum rate, the sum rate of error exponent pair. G is also the sum rate of the error exponent pair for when you use non-adaptive strategies. Okay. So to numerically compute f and g, especially g, as the first soup is taking over all finite sites. So if we don't have a clear cardinality bound, then we can't do the computation. Then we can't do the numerical evaluation for g. Okay. So fortunately, we can prove theorem 7. Theorem 7 basically says that to evaluate this function, we just need to take supremum or all set x whose cardinality is less than d squared. Okay, so this is the theorem 7. Okay, this is the numerical results. So here I take R1 and R2 is 0.98. So it's very close to pure space. This is the theta. We vary theta from 0 to pi over 2. Then we look at the sum rate f and g. Then we can see that clearly adaptive strategy is better than non-adaptive one. Okay. I need to point this out because for the fixed length case, Hayashi actually, in his famous paper, Discrimination of two classical channels, with application to discrimination of quantum states in that paper, actually he showed that adaptive strategy can't give you any advantage over non-adaptive ones. This is not true for the sequential case. In the sequential case, we will see adaptive strategy is better. Okay, this advantage is illustrated by the sum rate. Okay, so this can also be illustrated by the achievable regions. Okay, this region is the best you can do. This is the best you can do when you use non-adaptive strategy. This rectangle is this larger rectangle is the regions that you can do when you use adaptive strategies. Okay, this blue part is your advantage. So we also do the numerical evaluation for compared to the fixed length case. This is those two are comparison of the performance of adaptive and non-adaptive in the sequential setting. Okay, so this is a numerical example to show the performance when we try to discriminate two states here, the two cubic states. Sorry, I should use R0 and R1. Okay. Anyway, this is the R both are equal to 0.9. The theta is equal to pi over 2. Okay. So then we look at the performance of the different sets of tests. Okay. So the x-axis here, this is the number of samples we use. So the y-axis is the negative log of the error probabilities, as the error probability is very small. So I need to take the negative log to see the performance. Otherwise, it's very messy. So here SA is the sequential. Here SA stands for sequential quantum hypothesis test with adaptive strategies. SNA stands for sequential hypothesis test with non-adaptive strategy. This CUL stands for the collective measurements for the fixed length case. This FNA is the fixed length when you use non-adaptive strategy. So this FA is a fixed length case, but when you use adaptive strategy, which means you perform the measurement locally, but in an adaptive fashion. Okay. So we do the numerical simulation. For the sequential case, as the number of samples is a random variable. So this x-axis is actually the expectation, not the actual number of samples used. Okay. So we can see that for this one the sequential adaptive case is better. It's the best, has the best performance. Okay. Okay, so we can see from this and this we will see the sequential actually always perform better than the fixed length case, even for the collective measurement. Okay. So this is the collective measurement. This is the sequential case. This is the fixed length. This is a fixed length case. Okay, so we can always see that the sequential cases are better. Let me check the time. Should I stop here?
I think it's fine. You can finish. It's time. It's okay to extend a little. Yeah, you can finish it.
Okay. Okay. So yeah, I think we still have 5 to 10 minutes. So I will tell you the basic idea of the achievability part of the theorem 3. For theorem 3, we give a characterization of the region of achievable error exponents. So here, the main idea is we will construct a sequence of sequential quantum probability ratio tests. Okay. So before that, I will introduce two actually projector valued measurements. Those M0 star and M1 star, which those are two projector valued measurements. that achieve the supremum in the definition of the measured relative entropy. Okay, so we define this kind of ZJ. ZJ is actually the log likelihood ratio of each sample. Okay, so Sk is the log likelihood ratio. So to define a sequential quantum hypothesis test, we need to define two things. We need to define three things. One is the output alpha bit. Here is a fixed. Okay. So the second one is we need to define the conditional probability match function to basically we need to define a sequence of strategy to choose the next measurement based on the previous one. So this is our strategy to choose the measurement. Okay, equation. Okay, this is the equation 24 and equation 25 is the mathematical formula, but the idea is very simple. The idea is that so each time, like at time k minus 1, if we at time k minus 1, the measurement you choose for the next time is you just do a maximum likelihood estimation. Okay, you try to figure out which state give you the which state give you the larger probability for your current outcome and current measurement. Okay, so if you figure out that state, then you choose the corresponding measurement. Okay, so if it's 0, then we choose if it's 0, then we choose M0. If it's 1, then we choose M1. Okay, so this is the intuitive explanation of equation 24 and 25. So it's kind of like we first do a maximum likelihood estimation. Then based on this kind of maximum likelihood estimation, we choose the measurement. Okay. So this is as I said, we for sequential quantum hypothesis test, the third element is the sequence of test. Is a sequence of the sequence of decision functions. So as this is a sequential quantum probability ratio test, so if it's above this threshold, then we will stop and output 0. If it's very small, then we will stop and output 1. If it's not, then we continue the test. Okay. So this is our decision functions. The Tn is the number of samples for this test. An and Bn are the thresholds defined in this way. Tau is some very small number. Okay. Okay. So those are so to prove this result, we will show two things. The first is we will give bound on the error probabilities, and the second one we will show that actually our test satisfy the expectation constraints asymptotically. Okay. We'll prove two things. The first one is the bound on the error probabilities. So this is simple. This is kind of like this is from definition. Equation 1 is from definition. Okay. Equation 2 just write it in the write the probability using characteristic function to denote the expectation. So from equation 2 to equation 3, this is this is a tricky one. Kind of like you change the measurement. Sorry, this is a change of measure, not change of measurement. Okay, this is a change of measure. We change from the measure P0 to measure P1. We add the rhodonic diameter derivative here. Okay. Then we just use simple bound. Then at this is a characteristic function. Okay, this is less than this one, so we have this one. Similarly, we can find a bound on beta n. So this is the bound on the error probability. Then the second one is we need to show some. We need to show that our test actually satisfies the expectation constraints. Okay. So this is we define Tn height in this way. So we can see that Tn height is actually larger than Tn. Okay, then we will see. Then this is okay during some okay. Then this is use some some calculations. We will see that this is less than this one, and we have this is less than some. This is less than bn plus c. As t hat is the first time like this is larger than bn, so this one is less than bn. Here Zn we will show that this is under our assumptions. Zn is actually less than some constant. Okay, so this is a set of equations to show that this is a set of equations. Okay, this set of equations and the inequality to show that it's actually we actually satisfy this kind of constant. Okay, so as you can see in the end we have this one. So this is so we know this is a positive number when n is very large. So we will see that this expectation is actually strictly larger than n for sufficient large n. So our sequence of tests actually satisfy the expectation constraint. Okay, so from equation 2 to the third inequality here is actually we need to apply some optional theorem from martingale theory. Okay, I didn't put it here because it's if you're interested you can check our paper. So okay. So those two slides finish the proof of the attribute part. Okay, so this is the key lemma that we use as our result is optimal. So we always need to prove two kinds of results. The one is the attributability part. We construct a sequence of tests such that they saturate the bound, and the other direction is we need to prove converse. We need to show that for any sequence of tests, they don't violate, the achievable error probability should not violate our bound. Okay, so this is lemma 8 is from okay. So for any sequence of sequential quantum hypothesis test, if the expected number of samples is finite, then we can have this kind of inequality. Okay, this is the inequality related. This is the inequality related to the error probability to the number of samples used. Okay. I will skip this one. Okay. Oh, okay. I will finish the. Okay. So sorry, I skipped this slide. Okay. So if we have a sequence of tests which satisfy the expectation constraint, which means this one is less than n asymptotically, so we can just replace this one by n. Then we will see this one is less than this one. Then we will see this one is less than this one. As this are lim two, so it's okay. So we will see the convergence rate of the error probability is upper bounded by this one and this one, no matter what kind of sequential test you use. Okay. So this is the conclusion. So any achievable error exponent pair should satisfy those two inequalities. Okay. So the next three slides are the proof of lemma 8. So the basic idea is just we kind of apply some data processing inequality. Okay. So the proof of data processing inequality, we also need to use some optional some theorem from martingale theory. Okay. So that's all for my talk.
Okay, thank you very much for the nice talk. So any question or comments from the audience?
Yes, I have one. So is there a classical analog of all these results, like including the non-adaptive and the adaptive case?
Actually, yes, there are. So for quantum for classical hypothesis testing, there is analog of there is a sequential hypothesis testing proposed by Walt in the last century, 1945. So different from the classical hypothesis testing here is in the quantum setting is each time we need to choose a measurement. This measurement is kind of like an action. So this is kind of like there is one paper called active sequential hypothesis testing, proved by Professor Javadi from UC San Diego. So in that paper, they kind of have a classical formulation of this problem. They have a set of probability distributions. Each time they need to do an action, then they try to minimize the error probability plus the number of samples used. Okay, so there do exist. There is an analog of this problem.
I see. Also, one more follow-up. So in the classical case, is it also true that the adaptive is somewhat more powerful than the non-adaptive one?
I don't know. They didn't talk about it.
Oh, I see. Yeah, that's it. That's the question. Yeah, thanks.
Okay.
Sorry, I may have a naive question. I'm not sure if I understand it correctly. It looks like you can do the question in two ways. In the previous studies, they study given alpha n and beta n, and you quantify the size, the sample size t for some bounds. You just estimate that. And for your case, you are fixing or you limit the size t either in expectation or in probabilities, and you are trying to optimize R0 and R1.
Yeah.
Is that correct? So how do you define the optimal R0 and R1? So what's the how do you define optimal? You are trying to limit their size R0 and R1 as small as possible, or how do you say they are optimal?
Okay, so this is okay. So it's so from the definition here, this is the achievable error exponent pair. Okay, so for a sequence of tests, so we define the region. This region is the closure of all achievable error exponent pair. Okay, so no matter what kind of test you use, if you satisfy the expectation constraints, then your error exponent should be in this region. So our optimality is kind of like we figure out this region, what this region is. So if we can figure out the region, then we will see. This is not a one-dimensional problem. We can't find the this is a subset of R2, two-dimensional Euclidean space. So we can't. This is not in a one-dimensional space. So we need to figure out the whole region to see the optimality, not the largest rate or smallest rate.
So you find out the region through some strategy you find, or
yeah. This region. This region includes all the achievable error exponent pair. So this region includes all R0 and R1. Okay, so our goal is to try to figure out what this region is. To characterize this region, we prove kind of in information theory, we call it attributed part. We construct a sequence of tests that achieves some point of this region. So for the converse part, we show that this is a okay. This is a okay. Maybe I go this slide too fast. Okay, this is this Sn is any sequence of tests such that the error probability goes to 0, and the expectation of this the expectation of this test satisfies the expectation constant. Okay, then we try to find an upper bound on those two on those two quantity. Okay. So we see that actually we can use this kind of use lemma eta, and we can see that this is actually less than this point. So this is the rectangle formed by this corner point is actually an upper bound on the achievable error exponent pair. It's an upper bound on AE. Okay. The test we construct here. Okay. Yeah, this is the test that we construct here is actually achieves those 2 points as we define A and B in here. Okay, so we construct a sequence of tests which achieve that corner point. We also show that for any sequence of tests, the convergence rate of the error probability is upper bounded by those two numbers. So that's the proof of the optimality.
Yeah, I see. So you find the bound which is satisfied by the bound you choose in the beginning.
Yeah.
Okay. Okay, thank you. So any question from or comments from the audience?
Yeah, one more. So here we are trying to distinguish two states. Like, can we generalize these things to multi settings? Like, we have different hypotheses and want to see which is the right one, for example.
Yeah, this is actually our ongoing work. We have made some progress in this direction.
I see.
Yeah, this can be done. This can be generalized to multi-states. So one key point here is that for the fifth length case, it's very difficult to figure out the error exponents of the problem should be called multiple quantum hypothesis testing. So, but for the sequential case, actually we can figure out the error exponent for the multiple sequential quantum hypothesis testing.
Okay, interesting. So the non-adaptive one is much harder somehow, but adaptive one is
yeah,
more doable. Yeah.
Okay, thank you very much. I think if there's no further questions, so let's thanks Dr. Li again. Thank you. Yeah, thank you very much.
Okay.